Night settles over the planet in a way that feels ordinary to us. Cities dim slightly, the sky darkens, and slowly the first stars begin to appear. To most people, it feels like the same sky our ancestors saw thousands of years ago. A scattered pattern of distant lights, beautiful but quiet, hanging far above the noise of everyday life. But the sky is not showing us the present. It never has. Every point of light overhead is delayed. Every star, every galaxy, every faint smear of light is arriving late, carrying with it a message that began travelling long before anyone on Earth thought to look for it. Light moves quickly by human standards. It circles the Earth 7 times in a single second. It travels from the Moon to us in just over a second, and from the Sun in about 8 minutes. Those numbers feel fast, almost instantaneous. Yet when the distances grow large enough, even light begins to feel slow. When you look at the Sun, you are not seeing it as it is right now, you are seeing it as it was 8 minutes ago. If the Sun somehow vanished, the Earth would continue orbiting it normally for 8 minutes before the darkness arrived. The same rule applies everywhere in the universe. Light takes time to travel, and the universe is unimaginably large. The nearest star beyond our Sun, Proxima Centauri, sits just over 4 light-years away. The light you see from it tonight began its journey when you were 4 years younger than you are now. If you could somehow watch the star disappear at this moment, the night sky would continue showing it to you for 4 more years before the news reached Earth. Already the sky's beginning to look less like a place and more like a timeline. As the distances grow larger, the delays stretch into something much stranger. The bright star Vega shines from 25 light-years away. The Orion Nebula glows from roughly 1,300 light-years away. When that light began travelling toward us, human civilizations were still in the early Middle Ages, but stars are only the beginning of the story. When we look beyond our own galaxy, the scale changes completely. The nearest large galaxy to our own is Andromeda. Even though it appears faintly to the naked eye as a soft smudge of light in the northern sky, Andromeda is enormous. It contains hundreds of billions of stars and stretches across more than 200,000 light-years of space. Yet the light reaching our eyes from Andromeda tonight left that galaxy roughly 2.5 million years ago. When those photons began their journey toward Earth, the earliest ancestors of modern humans were still walking the African savannas. Stone tools were simple, fire was newly mastered, and language was only beginning to take shape. The entire span of human civilization, cities, writing, science, music, telescopes, has unfolded while those particular rays of light were quietly crossing intergalactic space. They arrive now, slipping through Earth's atmosphere and into our eyes without ceremony, carrying an image of Andromeda as it existed in a time when humanity itself was barely beginning. The deeper we look into the universe, the further back in time we travel. This idea sounds almost poetic, but it is also literal. Astronomers often say that telescopes are time machines, and unlike the fictional kind, these machines genuinely allow us to see the past. The reason is simple physics. Because light travels at a finite speed, distance and time become inseparable. Every telescope, no matter how small, is effectively looking backward. When Galileo first turned his telescope toward the sky in the early 17th century, he was not only seeing farther into space than any human had before, he was also seeing further into history. As telescopes grew larger and more powerful, this ability expanded dramatically. Each improvement allowed astronomers to capture light that had been travelling for longer and longer stretches of time. The Hubble Space Telescope, launched in 1990, pushed this concept to an extraordinary level. One of its most famous observations began almost by accident. astronomers pointed Hubble toward a tiny patch of sky that appeared completely empty. No stars, no visible objects, nothing interesting at all. For days, the telescope stared at that empty darkness. Slowly, faint specks of light began to appear on the image, then more of them, and more. When the final image was processed, what had once seemed like a blank region of space was revealed to contain thousands of galaxies, each one a vast system of stars, each one unimaginably far away. Some of those galaxies were so distant that the light we captured had been travelling for more than 12 billion years. That means the telescope was not merely photographing distant galaxies, it was capturing snapshots of the universe when it was still young, only a fraction of its current age. In those images, astronomers were not seeing the modern universe at all. They were seeing something closer to its childhood. The galaxies looked smaller, more chaotic, less organised than the ones we observed nearby. Some were in the process of forming, others were colliding, merging, reshaping themselves under the pull of gravity. The deeper we look into space, the less familiar the universe becomes. In a very real sense, the night sky contains layers of history stacked on top of one another. Nearby stars show us the relatively recent past. Distant galaxies reveal ancient epochs. The faintest objects detectable by modern telescopes allow us to peer almost all the way back to the beginning of cosmic structure itself. And there is something quietly unsettling about this realization. The universe we observe is not happening all at once. It is a collage of moments separated by enormous spans of time. One galaxy might appear exactly as it existed 50 million years ago. Another might show us conditions from billions of years earlier. In a single telescope image, astronomers are often looking at objects that belong to completely different eras of cosmic history. The sky is not a photograph. It is a mosaic of ancient messages arriving at different times. Some of those messages began their journey long before our planet formed, long before the sun ignited, long before the Milky Way itself had fully taken shape, and occasionally the message may be the only trace of something that no longer exists. Stars live long lives by human standards, but even they eventually fade. Galaxies evolve, collide, and transform over billions of years. Entire cosmic structures change slowly, reshaping themselves under gravity's influence. Because light takes time to travel, we may still be seeing galaxies whose present form has already changed dramatically. In extreme cases, the galaxy we observe may have already merged with another one, altered beyond recognition, or faded into a quieter state long after the light left it. The universe we see is therefore slightly out of date. We are always watching history. Astronomers sometimes describe this in a gentle way, saying that when we observe distant galaxies, we're studying the early universe. But the deeper truth is even more fascinating. The night sky is not simply a window into space, it is a record. A vast, slowly arriving archive of everything the universe has ever been. Every photon carries information about the moment it left its source. Its colour, its direction, its subtle shifts in wavelength, all contain clues about the environment that produced it. By studying these faint signals carefully, scientists can reconstruct events that occurred billions of years ago. The birth of stars, the growth of galaxies, the expansion of space itself, all of it written into light that has been travelling longer than human civilization has existed. Once you begin thinking about the sky this way, the quiet beauty of distant galaxies takes on a completely different character. Those faint spirals and glowing clouds are not simply remote objects, they are survivors of time, messages that have crossed unimaginable distances without interruption, moving steadily through the darkness while entire worlds formed, evolved, and disappeared along the way. Tonight, as you look upward, photons that began their journey millions or billions of years ago are arriving on Earth. They slip quietly through the atmosphere, pass unnoticed through the air, and land on telescopes, cameras, and human eyes. Each one carries a tiny piece of history, and together they form the strange and beautiful illusion we call the night sky. For a long time, the idea that the night sky was a record of ancient light would have sounded almost meaningless to the people who first studied it carefully. They saw the same sky we see today, but the scale of what they were looking at remained hidden behind a quiet assumption that lasted for centuries. To early astronomers, the stars seemed distant, but not unimaginably so. They appeared arranged across the inside of a vast sphere surrounding the Earth, fixed into place like small lanterns embedded in a dome. Even after the realization that Earth orbits the Sun replaced older geocentric ideas, the broader picture of the universe remained strangely compact. The stars formed a system. The Milky Way was a kind of grand celestial structure, and beyond that, perhaps nothing at all. The faint cloudy band stretching across the sky had fascinated observers since antiquity. Ancient Greek philosophers speculated that the Milky Way might be composed of distant stars packed so closely together that the eye could not distinguish them individually. But even as telescopes improved and confirmed that the Milky Way was indeed made of countless stars, astronomers still tended to imagine it as the entire universe. It was a vast island of light surrounded by emptiness. The notion that other systems like it might exist was occasionally suggested, but it remained speculative and uncertain. When early telescopes revealed faint smudges of light scattered across the sky, astronomers catalogued them carefully. These objects became known as nebulae, a word simply meaning clouds. Some nebulae resolved into star clusters when viewed with larger instruments, confirming that they were nearby structures inside the Milky Way. Others, however, remained stubbornly blurred. No matter how powerful the telescope became, these objects refused to break apart into individual stars. Their light appeared soft and continuous, sometimes shaped into delicate spirals or faint glowing ovals. The most famous of these was a pale patch in the constellation Andromeda. Observers had recorded it for centuries, noting its presence as a faint misty glow. With early telescopes it appeared larger and more complex, but its true nature remained mysterious. Was it a gas cloud forming new stars inside the Milky Way? Was it some unusual structure within our own galaxy that telescopes simply could not resolve? Or was it something else entirely? By the late 19th and early 20th centuries, this question had grown into one of the most important debates in astronomy. The spiral nebulae, as they were often called, displayed intricate shapes when photographed with long exposures. Their spiraling arms suggested structure and motion. Some astronomers began to suspect that these objects might be entire stellar systems similar to the Milky Way itself, unimaginably distant and far beyond our galaxy's boundaries. If that interpretation were correct, the universe would instantly become far larger than anyone had previously imagined. But proving such a claim required more than speculation. Distances in space are notoriously difficult to measure. Astronomers can determine how bright an object appears, but brightness alone does not reveal distance. A faint object might be dim because it is small or because it is far away. Without an independent method of determining distance, the spiral nebulae remained ambiguous. The debate reached a turning point in April of 1920 during a public event held at the Smithsonian Museum of Natural History in Washington, D.C. Known later as the Great Debate, it brought together two prominent astronomers, Harlow Shapley and Heber Curtis, to argue opposing interpretations of the universe's structure. Shapley believed that the Milky Way was enormous and contained everything in existence. In his view, the spiral nebulae were simply nearby structures inside our galaxy. Curtis argued the opposite. He proposed that the spiral nebulae were distant, island universes, each one a separate galaxy comparable in size to the Milky Way but located far beyond it. The debate itself did not settle the issue. Both sides presented evidence, and neither could definitively prove their case at the time. But the conversation crystallized a profound question. Was the Milky Way the whole universe, or merely one component within a much larger cosmic landscape? The answer arrived only a few years later through the work of a young astronomer named Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble had access to the most powerful telescope of the era, the 100-inch Hooker telescope. Its mirror gathered far more light than earlier instruments, allowing astronomers to examine distant objects in unprecedented detail. Hubble turned this telescope toward the Andromeda Nebula, the same faint smudge that had puzzled observers for centuries. Instead of simply photographing its spiral arms, he began searching for specific types of stars known as Cepheid variables. These stars have a remarkable property. Their brightness changes in a regular pattern over time, brightening and dimming in predictable cycles. Even more useful, the period of that cycle is directly related to the star's true brightness. By measuring how long a Cepheid takes to vary, astronomers can determine how luminous it actually is. Once the true brightness is known, comparing it to how bright the star appears from Earth reveals its distance. It is one of the first reliable methods ever developed for measuring the vast scales of the universe. In 1923, while examining photographic plates of Andromeda, Hubble noticed a tiny point of light that changed brightness between exposures. At first, he suspected it might be a nova, a star briefly flaring brighter before fading again. But as more observations accumulated, the pattern became unmistakable. The star was not a nova, it was a Cepheid variable. When Hubble calculated its distance using the known relationship between its brightness and its variation period, the result was astonishing. The star was far too distant to belong to the Milky Way. In fact, it lay more than 2 million light-years away. That single measurement changed everything. If a star inside the Andromeda Nebula was millions of light-years distant, then the nebula itself had to be an entire galaxy, vastly separated from our own. The Milky Way was not the universe. It was one galaxy among many. The implications were enormous. Suddenly, the faint smudges scattered across astronomical photographs were no longer nearby curiosities. Each one represented a colossal system of stars, gas, and dust, occupying its own region of space. The scale of the universe expanded almost overnight. What had once seemed like a single cosmic structure now became a vast collection of galaxies stretching across unimaginable distances. As telescopes continued improving, astronomers discovered more and more of these distant systems. Photographic plates revealed thousands of galaxies where earlier observers had seen only darkness. Later surveys counted millions, then hundreds of millions. Today, with modern telescopes capable of detecting extremely faint objects, scientists estimate that the observable universe contains at least 2 trillion galaxies. Each one is a gravitational city of stars, sometimes containing billions or even trillions of suns. Each one has its own history of formation, collisions and transformation, unfolding over billions of years. This realization reshaped humanity's understanding of its place in the cosmos. Earth was no longer part of a single stellar system surrounded by emptiness. Instead, our planet resides within one galaxy among an immense population scattered across the universe. The Milky Way itself suddenly appeared less like the entire cosmos and more like a neighborhood within a far larger cosmic landscape. And once that shift in perspective occurred, the sky began to look different again. Those faint smudges of light scattered across telescope images were no longer small or insignificant. They were vast structures seen from extraordinary distances. Entire galaxies were quietly shining across the darkness, their light beginning its journey millions or billions of years before it finally reached us. The same principle that makes the night sky a time machine also allowed astronomers to glimpse these remote systems as they existed long ago. In some cases, the galaxies we observe today may have already evolved into something entirely different, their ancient appearance preserved only in the light that continues to travel toward Earth. This discovery did more than expand the size of the universe. It transformed astronomy itself. Instead of studying a single galaxy, scientists were now confronted with a population of galaxies, each with unique properties, histories, and structures. The cosmos was no longer a solitary system, but a vast community of galaxies, interacting through gravity across unimaginable scales. And as telescopes continued reaching deeper into space, the realization from Hubble's discovery only grew more dramatic. Every time astronomers examined a seemingly empty patch of sky, with enough sensitivity, they found more galaxies hiding there, faint and distant, waiting to be revealed. The universe, it turned out, was far richer and more expansive than even the most ambitious astronomers had suspected. And the light from those galaxies was already on its way to us, traveling patiently across billions of years, adding new layers to the quiet historical record written across the night sky. Once the realization settled in that the faint spirals scattered across the sky were entire galaxies, the next question followed naturally, almost inevitably. If these distant systems were real, if they were not clouds or nearby curiosities, but enormous stellar worlds far beyond our own, then what exactly were they made of? From a distance, a galaxy appears calm, even serene. Long exposures reveal graceful spirals, glowing ovals, faint halos of light suspended quietly in the dark. They look like objects frozen in place, almost like celestial paintings. But that impression is deceptive. A galaxy is not a solid structure. It is not a single object in the way a planet or a star is. It is something far more dynamic and complex, something closer to a slow, unfolding ecosystem of matter and gravity operating across unimaginable scales of time. The Milky Way itself offers the closest example. Our galaxy stretches across roughly 100,000 light-years from one side to the other. Inside that vast span reside somewhere between 100 and 400 billion stars, depending on how they are counted. Each one is a separate sun, many with their own planets, their own systems of orbiting worlds. If the Milky Way could somehow be shrunk to the size of North America, the distance between neighboring stars would still be measured in hundreds of kilometers. The scale is so large that even a galaxy filled with billions of stars remains mostly empty space. The stars themselves are only the most visible part of the story. Between them lies a mixture of gas and dust, thin but widespread, drifting slowly through the galaxy in enormous clouds. These clouds are known as nebulae, and although they appear delicate in photographs, they are often vast structures stretching for dozens or even hundreds of light years. Inside them, gravity gradually gathers matter together, compressing the gas until new stars begin to form. The birth of a star is not a sudden event but a long process unfolding over millions of years. A region within a nebula slowly collapses inward under its own weight, becoming denser and hotter as material falls toward the center. Eventually, the pressure and temperature become so extreme that nuclear fusion ignites, and a new star begins shining. Around it, leftover material flattens into disks that may eventually become planets, moons, asteroids, and comets. In this way, galaxies continuously recycle their contents. Old stars eventually die, releasing heavy elements into the surrounding space through stellar winds or supernova explosions. Those elements mix with gas clouds and become the raw material for future generations of stars and planetary systems. The atoms inside your body were once forged in the cores of stars that lived and died long before the sun was born. When astronomers describe galaxies as evolving systems, this is what they mean. Stars are constantly being created, aging and disappearing, while gas flows through the galaxy like a slow cosmic weather pattern. Over billions of years, the overall structure changes gradually as gravity reshapes the distribution of matter. Gravity is the quiet force that holds everything together. Without it, the stars inside a galaxy would simply drift apart into empty space. Each star is moving through the galaxy at tremendous speed, often hundreds of kilometers per second, following an orbit around the galactic center. The Sun itself completes one full circuit around the Milky Way roughly every 230 million years. Since its formation about 4.5 billion years ago, our star has completed only about 20 such orbits. Yet gravity somehow keeps this enormous system bound together, preventing it from dissolving into the surrounding universe. For a long time, astronomers believed that the visible matter within galaxies, the stars and gas clouds we can observe directly, must provide enough gravitational pull to hold everything in place. But when they began measuring the motion of stars in detail, something strange appeared. The outer regions of galaxies were moving too quickly. According to the laws of physics, stars far from the galactic center should orbit more slowly, much like planets farther from the Sun move at lower speeds. Instead, stars at the edges of galaxies were racing along almost as fast as those near the center. This implied that galaxies contained far more mass than their visible stars and gas could account for. Something else had to be there. Something invisible but massive enough to influence the motion of everything around it. That hidden component is now known as dark matter. No telescope has ever seen it directly. It does not emit light, reflect light, or absorb light in ways we can easily detect. Yet its gravitational influence appears everywhere astronomers look. When scientists map the motion of stars inside galaxies, or measure how galaxies interact with one another, the calculations consistently show that most of the mass must belong to this unseen substance. In fact, the visible parts of a galaxy may represent only a small fraction of its total mass. Surrounding the luminous disk of stars lies an enormous halo of dark matter, extending far beyond the region where stars are found. This halo forms the true gravitational backbone of the galaxy, anchoring the stars and gas within its invisible reach. In this sense, what we usually picture as a galaxy is only the bright center of a much larger structure. The familiar spiral arms of the Milky Way, the glowing core, the clusters of stars scattered across the sky, are all embedded inside a much larger envelope of unseen matter that stretches hundreds of thousands of light years outward. Within this vast framework, stars move like tiny sparks carried by slow currents of gravity. Their individual lifetimes may last billions of years, Yet compared to the age of the galaxy itself, even those lifetimes are brief episodes, a galaxy is, therefore, less like a machine and more like a long-lived environment, continuously reshaped by the movement of matter and the passage of time. The spiral arms of galaxies illustrate this beautifully. When people first see images of spiral galaxies, they often imagine the arms as fixed structures, like the blades of a rotating pinwheel. But that is not quite how they behave. The stars inside those arms are not permanently attached to them. Instead, the arms are regions where density waves pass through the galaxy, slightly compressing the gas and dust as they move. As this compression occurs, new stars form in clusters, lighting up the spiral pattern temporarily. Over time, those stars drift away, while new ones appear elsewhere along the arm. This spiral shape persists, but the individual stars within it are constantly changing. This process unfolds slowly, far too gradually to observe within a single human lifetime. Yet across tens or hundreds of millions of years, the structure evolves continuously. Star-forming regions ignite and fade. Gas clouds collapse and disperse. Entire clusters of stars migrate through the galaxy, following orbits that shift subtly as gravitational interactions accumulate. Even the central regions of galaxies are dynamic places. Many galaxies contain dense bulges of older stars near their centers, while some harbour active supermassive black holes that influence the surrounding environment. Streams of gas can spiral inward toward these central regions, feeding bursts of star formation or fueling energetic phenomena that send radiation streaming across the galaxy. When astronomers observe galaxies at different distances, they are effectively seeing different stages of this ongoing evolution. Nearby galaxies show us relatively mature structures, systems that have had billions of years to settle into stable forms. More distant galaxies, whose light left them when the universe was younger, often appear more chaotic with irregular shapes and turbulent star-forming regions. These differences are not random. They are glimpses of the galaxy's long story unfolding over cosmic time. In the early universe, galaxies were smaller and more irregular. Gravity gradually drew them together, merging smaller systems into larger ones. Collisions and interactions reshaped them again and again, producing the diverse population we observe today. Some galaxies grew into elegant spirals like the Milky Way. Others became smooth elliptical giants composed mostly of older stars. Still others remain irregular and scattered, their structures disrupted by past encounters with neighbouring galaxies. Through all of these transformations, the basic ingredients remain the same: stars, gas, dust, dark matter, and gravity guiding their motion across billions of years. The more astronomers study galaxies, the more they begin to resemble living systems in the broadest sense of the word. Not alive in the biological sense, of course, but active, evolving, continuously exchanging matter and energy with their surroundings. New stars ignite while old ones fade. Gas clouds drift, collapse, and disperse. Entire regions of the galaxy grow quiet while others burst into sudden brilliance, and all of it unfolds on timescales so vast that human history barely registers as a brief moment within the life of a single star. When we step back and look at a galaxy from afar, the result appears calm and orderly, a graceful swirl of light suspended in darkness. Yet inside that quiet glow lies an intricate web of processes that have been unfolding for billions of years, slowly shaping the architecture of the universe. The galaxies that Hubble revealed as distant island universes are not static islands at all. They're enormous gravitational ecosystems where matter drifts, gathers, ignites and fades in a slow cosmic rhythm that has been playing since the universe itself was young. If galaxies are vast ecosystems of stars and gas drifting through space, the next mystery becomes unavoidable. What is actually holding them together? When astronomers first began measuring the motion of stars inside galaxies in detail, the results were quietly unsettling. These stars were moving far too fast. To understand why this mattered, imagine watching a small object orbiting something much larger. A planet circles a star because gravity pulls it inward, while its motion carries it forward. The balance between these two influences determines how quickly the planet must travel. The farther it is from the central star, the weaker the gravitational pull becomes, and the slower the orbit should be. This simple relationship works beautifully within our solar system. Mercury races around the Sun in just 88 days, while distant Neptune takes more than a century to complete one orbit. Distance weakens gravity, and motion slows accordingly. Astronomers expected galaxies to behave in the same way. The stars near a galaxy's centre should move quickly, pulled strongly by the combined gravity of the stars packed into that region. Farther out, where the visible stars grow sparse, the gravitational grip should weaken and the outer stars should drift along more slowly. But when scientists carefully measured the speeds of those distant stars, they found something different. Instead of slowing down, the stars at the outer edges of galaxies were moving almost as quickly as those much closer to the centre. In some cases, they were travelling so fast that, according to the visible mass of the galaxy, they should have escaped entirely and flown off into intergalactic space. Yet they did not. They remained bound to the galaxy, continuing their long, slow orbits as though an enormous invisible weight were holding everything together. This discovery emerged gradually throughout the 20th century, but it was the work of astronomer Vera Rubin in the 1970s that brought the evidence into sharp focus. Rubin studied the rotation of spiral galaxies with remarkable precision, mapping how fast stars were moving at different distances from the galactic centre. The patterns she found were impossible to ignore. The rotational speed of galaxies remained almost constant far beyond the regions where most visible stars and gas existed. It was as though the galaxy were embedded inside a much larger unseen structure whose gravity dominated the system. This hidden component came to be known as dark matter. The name itself is simple, almost understated. Dark because it does not emit or reflect light in ways our telescopes can detect. Matter because its gravitational influence behaves exactly as mass should. Whatever dark matter is made of, it interacts with the universe primarily through gravity. It does not form stars or planets, and it does not glow. Yet its presence can be traced by the way galaxies move and bend light around them. One of the most powerful pieces of evidence comes from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of space itself. Light travelling near such objects follows curved paths, bending as it passes through the distorted geometry around them. When astronomers observe distant galaxies through the gravitational influence of a massive foreground galaxy or cluster, the background light becomes stretched, magnified, or even duplicated into arcs and rings. By carefully measuring these distortions, scientists can map how mass is distributed within the foreground object. Again and again, these maps reveal far more mass than can be explained by visible matter alone. Vast halos of unseen mass surround galaxies and galaxy clusters, extending far beyond the regions where stars are found. In many cases, the dark matter halo contains several times more mass than the luminous galaxy embedded within it. It is as though the stars we see are only the bright centre of a much larger invisible structure. Once astronomers began accounting for this hidden mass, the behaviour of galaxies suddenly made sense. The stars are not flying apart because they are orbiting inside enormous halos of dark matter whose gravity extends far beyond the visible disk. But the implications of dark matter reach even further. When scientists simulate the formation of galaxies in computer models of the early universe, something fascinating appears. In the aftermath of the Big Bang, matter was not perfectly evenly distributed. Tiny fluctuations in density existed, regions where slightly more matter gathered than in neighbouring areas. Over time, gravity amplified those small differences. Matter slowly flowed toward denser regions, building larger structures. But ordinary matter alone, the atoms that form stars and gas clouds, would have struggled to assemble galaxies quickly enough to match what we observe today. Dark matter changes that story completely. Because it interacts only weakly with radiation, dark matter began clumping together long before ordinary matter could cool and collapse. These early dark matter concentrations acted like gravitational seeds. Gas gradually fell into their invisible wells, cooling and condensing until the first stars ignited. In this picture, dark matter forms the scaffolding upon which galaxies are built. The visible structures we admire in telescope images are only the luminous highlights tracing out a deeper invisible architecture. As computer simulations improved and observational surveys expanded, astronomers began noticing that galaxies themselves are not randomly scattered throughout the universe. Instead, they follow a striking pattern. When mapped across enormous distances, galaxies arrange themselves along long filaments that stretch for hundreds of millions of light years. These filaments intersect at dense nodes where massive clusters of galaxies reside. Between them lie vast empty regions, called cosmic voids, where very few galaxies exist at all. The resulting structure resembles a vast web. Delicate threads of galaxies span the universe, surrounding enormous cavities that appear almost completely empty. This pattern is now known as the cosmic web. It is one of the largest structures known to exist, stretching across the observable universe in a network of filaments and clusters. When astronomers compare observations of this web to simulations of dark matter in the early universe, the resemblance is striking. The same filaments appear in both. The same nodes of dense structure emerge where multiple strands intersect. The galaxies themselves seem to follow the underlying distribution of dark matter almost perfectly, tracing its invisible shape across cosmic distances. In this sense, the universe has a kind of hidden skeleton. Dark matter forms the framework, and galaxies illuminate it like tiny lanterns strung along its threads. Without that framework, the universe would likely look very different. Galaxies might have formed much later, or perhaps not at all. The delicate structures we see today might never have had time to assemble before cosmic expansion carried matter too far apart. Even now, scientists do not yet know exactly what dark matter is made of. Many theories propose new kinds of particles that interact weakly with ordinary matter. Experiments deep underground attempt to detect these particles directly as they pass through detectors shielded from cosmic radiation. Others search for indirect signals in space, hoping that dark matter particles might occasionally collide and produce detectable radiation. So far, the results remain inconclusive. The nature of dark matter continues to be one of the greatest unsolved questions in physics. Yet its gravitational influence is unmistakable. Every galaxy we observe appears embedded within its invisible halo. Every cluster of galaxies shows evidence of enormous hidden mass binding it together, even The overall pattern of cosmic structure across billions of light years reflects the distribution of dark matter in the early universe. When we step back and consider the full picture, the familiar luminous universe begins to look almost like a surface phenomenon. The stars, nebulae, and galaxies that fill astronomical photographs represent only a small fraction of what is actually there. Beneath that glowing layer lies a far larger network of unseen matter, quietly shaping everything we observe. Galaxies drift along the filaments of this structure like beads sliding along invisible threads. Over billions of years, gravity pulls them together, guiding their motions in ways that only become apparent when we observe the universe at its largest scales. And when we look deep into space, we're not only seeing distant galaxies shining across the darkness, we're glimpsing the faint outline of the cosmic web itself, illuminated by the galaxies that formed along its hidden pathways. Once the idea of an invisible cosmic framework takes hold, the mind naturally drifts further backward in time. If galaxies follow the hidden scaffolding of dark matter, then those structures must have begun forming very early in the history of the universe. The galaxies we see today, with their elegant spirals and dense clusters of stars, are the result of billions of years of gradual evolution. But there was a time when none of them existed yet. There was a moment when the universe contained no galaxies at all. To imagine that time requires stepping back to the very beginning of cosmic history. About 13.8 billion years ago, the universe was born in an event we now call the Big Bang. The phrase itself can be misleading, suggesting an explosion in space, but the reality was stranger. Space itself was expanding, carrying matter and energy outward as the universe grew larger and cooler. In its earliest moments, the universe was unimaginably hot and dense, filled with a glowing plasma of particles moving at extreme energies. Light could not travel freely then. Photons scattered constantly off charged particles, bouncing through the dense fog of the young cosmos. The universe was opaque, more like the interior of a star than the empty space we see today. As the universe expanded, it gradually cooled. After about 380,000 years, the temperature had fallen enough for protons and electrons to combine into neutral hydrogen atoms. When that happened, the fog lifted. Photons were suddenly able to travel freely across space for the first time. Those ancient photons still exist today as the cosmic microwave background radiation, a faint glow filling the entire universe and serving as one of the oldest observable relics of cosmic history. But even after light began traveling freely, the universe was still a very different place from the one we inhabit now. There were no stars yet, no galaxies, no planets or nebulae. The cosmos consisted almost entirely of hydrogen and helium gas drifting through space, slowly spreading as expansion continued. This long quiet period that followed is often called the Cosmic Dark Ages. The name does not imply violence or chaos. Instead, it describes a time when the universe contained matter, but no luminous objects to illuminate it. Hydrogen gas filled the cosmos, but nothing had yet condensed into stars bright enough to shine across the darkness. During this era, gravity was quietly at work. The tiny density fluctuations that existed from the earliest moments of the universe were beginning to grow. Regions containing slightly more matter than average slowly pulled in additional material from their surroundings. Dark matter played a crucial role in this process. Because it interacted weakly with radiation, dark matter was able to begin collapsing into dense structures earlier than ordinary matter could. These invisible clumps formed the first gravitational wells, the early seeds of cosmic structure. Over time, hydrogen gas fell toward those wells. the gas cooled and condensed, gradually forming dense pockets within the larger dark matter halos. These pockets would eventually ignite into the first stars. The birth of the first stars marked a turning point in the history of the universe. These early stars were likely very different from the ones we see around us today. Astronomers refer to them as population 3 stars, a name reflecting their position as the first generation of stellar objects. Because the early universe contained almost nothing except hydrogen and helium, these stars formed without the heavier elements that later generations inherited from earlier stellar explosions. Without those heavier elements to help cool the gas during star formation, the first stars may have grown extremely large. Some models suggest that many of them were hundreds of times more massive than our Sun. Massive stars burn their fuel quickly, shining intensely but living short lives. Instead of surviving for billions of years like the Sun, these early giants may have lived only a few million years before collapsing or exploding. Yet during those brief lifetimes, they transform the universe in profound ways. Inside their cores, nuclear fusion created the first heavy elements. Carbon, oxygen, nitrogen, and other atoms essential for future stars, planets, and eventually life were forged in these stellar furnaces. When the first stars died, many of them exploded as powerful supernovae, scattering those newly formed elements into the surrounding gas. This enrichment changed the chemistry of the universe permanently. Subsequent generations of stars would form from gas clouds already seeded with heavier elements, allowing them to develop more complex structures and longer lifetimes. The radiation from those first stars also began transforming the surrounding universe. Ultraviolet light streamed outward, ionizing hydrogen gas and gradually clearing away the darkness that had filled the cosmos for hundreds of millions of years. This process, known as cosmic reionization, slowly spread across the universe as more stars ignited. Regions that once contained cold, neutral hydrogen became filled with ionized gas, allowing light to travel more freely across vast distances. During this same period, the first galaxies were beginning to take shape. They did not appear suddenly as fully formed spirals or elliptical systems. Instead, they grew slowly through a series of mergers and accretions. Small clusters of stars formed within early dark matter halos. Gravity drew these clusters together, merging them into larger structures over time. Gas continued falling inward from the surrounding cosmic web, feeding ongoing star formation and gradually building more complex galaxies. In many ways, the earliest galaxies were chaotic places. Their shapes were irregular, often lacking the graceful symmetry we associate with mature galaxies today. Star formation occurred in bursts triggered by collisions and inflows of gas. Supernova explosions stirred the surrounding medium, sending shock waves through gas clouds and influencing where new stars could form next. Observing these ancient systems directly is extremely challenging. Because their light has been travelling for more than 13 billion years, it arrives at Earth incredibly faint and stretched toward longer wavelengths by the expansion of space. For decades, astronomers relied on powerful telescopes like the Hubble Space Telescope to glimpse these distant galaxies. Hubble revealed some remarkably early systems, allowing scientists to study galaxies that existed when the universe was less than 1 billion years old. But even Hubble had its limits. The most distant galaxies were simply too faint and too redshifted to observe clearly with its instruments. That situation changed dramatically with the launch of the James Webb Space Telescope. Designed specifically to observe infrared light, Webb can detect the stretched wavelengths emitted by some of the earliest galaxies in cosmic history. Almost immediately after beginning operations, the telescope started revealing objects that pushed the boundaries of what astronomers thought possible. Some of the galaxies Webb detected appear to have formed only a few 100 million years after the Big Bang. In cosmic terms, that is astonishingly early. It suggests that the process of galaxy formation began sooner and progressed faster than many earlier models predicted. These ancient systems often appear surprisingly mature, with significant numbers of stars already present despite the youth of the universe at that time. Webb's images show faint clusters of galaxies existing at times when the cosmos was still emerging from its earlier stages of structure formation. The light we observe from them today began its journey when the universe itself was only a few % of its current age. In a very real sense, telescopes like Webb allow astronomers to watch the universe learning how to build galaxies. The earliest examples are small and irregular. Over time they merge and grow, gradually assembling the larger systems that dominate the universe today. This process continues even now. Galaxies still collide, merge and evolve, though at a slower pace than during those early chaotic epochs. When we observe distant galaxies whose light has travelled for billions of years, we're not merely studying remote objects. We're witnessing earlier chapters of a story that eventually led to the Milky Way, the Sun, and the planet we now call home. The atoms inside our bodies were forged in stars that formed long after those first galaxies ignited, yet the chain of events connecting those moments stretches all the way back to the early universe. And so the faint galaxies revealed by our most powerful telescopes are not only distant in space, they are ancient milestones in the long unfolding process by which the universe gradually assembled the structures we see around us today. By the time galaxies begin appearing clearly in the early universe, they do not yet resemble the elegant structures that fill modern astronomy photographs. The first galaxies were small, uneven gatherings of stars and gas, still assembling themselves through gravity and frequent collisions. They were less like the calm spirals we admire today, and more like busy construction zones where matter was constantly arriving, merging, and rearranging itself. Over billions of years, those early systems gradually evolved into the astonishing variety of galaxies we now observe. When astronomers classify galaxies, they often group them into several broad categories, but these categories are not separate species the way plants or animals might be. Instead, they represent different stages and histories in the long life stories of galaxies. The shape a galaxy takes today is usually the result of everything that has happened to it in the past. One of the most familiar forms is the spiral galaxy. The Milky Way itself belongs to this family. When viewed from above, spiral galaxies resemble vast pinwheels of light. Long, curving arms stretch outward from a central bulge, wrapping around the galaxy's center in graceful arcs. Within these arms lie dense clouds of gas and dust where new stars are constantly forming. The arms glow with clusters of young blue stars, whose brightness briefly illuminates the spiral pattern before they drift away into the galaxy's broader disk. The central region of a spiral galaxy often appears brighter and more crowded with stars. Here the stellar population tends to be older, composed of stars that formed billions of years ago and have gradually migrated toward the galactic center over time. Surrounding the entire structure is a faint halo containing older stars and globular clusters, all embedded within the much larger halo of dark matter that governs the galaxy's gravitational behavior. Spiral galaxies are not rigid structures. The arms themselves are not fixed objects rotating like the blades of a fan. Instead, they are regions where density waves pass through the disk of the galaxy, briefly compressing gas clouds and triggering star formation. As stars ignite inside these regions, they illuminate the spiral arms temporarily. Over time, those stars move onward in their orbits, while new stars form elsewhere along the arm. The overall spiral pattern persists, even though the individual stars within it are constantly changing. This dynamic process means that spiral galaxies are often places of ongoing activity. Gas flows through their disks, stars are born in bright nebulae, and stellar winds and supernova explosions continually stir the surrounding material. These galaxies are often described as youthful in astronomical terms, not because they formed recently, but because they still possess the raw material needed to create new generations of stars. Not all galaxies remain so active. Some appear very different. Elliptical galaxies, for example, lack the dramatic spiral arms that make their cousins so visually striking. Instead, they appear as smooth, rounded clouds of starlight. Their shapes range from nearly spherical to elongated ellipses, but they generally lack the thin disks and structured arms of spiral systems. Inside elliptical galaxies, star formation has largely ceased. Most of the stars within them are older, reddish stars that have been shining for billions of years. The gas and dust needed to create new stars are mostly gone, either consumed long ago or expelled by energetic events in the galaxy's past. As a result, elliptical galaxies often appear calmer and more uniform. Their stars move in many different directions, creating a smooth distribution of light without the organized rotation seen in spiral disks. Many of the largest galaxies in the universe belong to this category. Giant elliptical galaxies often reside at the centers of galaxy clusters, where repeated mergers with smaller galaxies over billions of years have gradually built them into enormous stellar systems. Some of these giants contain trillions of stars and stretch across hundreds of thousands of light years. In contrast, irregular galaxies refuse to fit neatly into either of these categories. They lack the ordered spirals of disk galaxies and the smooth symmetry of ellipticals. Instead, they appear scattered and chaotic, their stars and gas arranged in uneven clumps without a clear overall structure. Irregular galaxies are often smaller systems whose shapes have been disturbed by gravitational interactions with neighboring galaxies. Close encounters can stretch them into distorted forms, pulling streams of stars outward and triggering bursts of star formation within compressed gas clouds. Sometimes these interactions leave galaxies permanently altered, their former structures replaced by irregular patterns that reveal the violence of their past encounters. The Large Magellanic Cloud, satellite galaxy orbiting the Milky Way, is a well-known example of an irregular galaxy. Visible from the southern hemisphere as a faint patch of light in the night sky, it contains vigorous star-forming regions and complex structures shaped partly by the gravitational influence of our own galaxy. Even smaller than these systems are dwarf galaxies, the quiet residents of the cosmic landscape. Dwarf galaxies contain far fewer stars than large spirals or ellipticals, sometimes only a few million or a few billion. Compared to the Milky Way's hundreds of billions of stars, they are tiny systems, yet they are extremely important for understanding how galaxies form and evolve. Many astronomers believe that large galaxies grew partly by absorbing smaller dwarf galaxies over time. Evidence of this process can be seen in the Milky Way itself. Streams of stars discovered in the outer regions of our galaxy appear to be the remnants of dwarf galaxies that were gradually torn apart by the Milky Way's gravity. Their stars now drift through our galaxy's halo, preserving faint traces of those long-ago encounters. Dwarf galaxies also provide valuable clues about dark matter. Because they contain relatively few stars, the gravitational influence of dark matter becomes especially noticeable when astronomers measure the motions of stars inside them. Many dwarf galaxies appear to be dominated by dark matter. making them excellent laboratories for studying the invisible substance that shapes cosmic structure. When astronomers examine galaxies across the universe, they see examples of all these forms. Some galaxies spin gracefully with bright spiral arms. Others appear as massive elliptical clouds of ancient stars. Still others show irregular patterns or remain small and faint as dwarfs. Yet these categories are not permanent states. Over billions of years, galaxies can change from one type to another as their histories unfold. A spiral galaxy that collides with another of similar size may lose its ordered disk entirely. The collision disrupts the delicate spiral structure, scattering stars into new orbits and compressing gas clouds in ways that trigger intense bursts of star formation. Eventually, the merged system may settle into a more rounded elliptical shape. In this way, elliptical galaxies are often thought to be the descendants of past mergers between spirals. The universe provides many examples of galaxies caught in the act of transformation. Telescopes occasionally capture images of two spiral galaxies in the process of merging, their arms stretched into long tidal tails by gravitational forces. Streams of stars arc outward into space, forming delicate bridges and loops that reveal the complex dance of gravity at work. Over time, these interacting galaxies will gradually combine into a single larger system. On smaller scales, dwarf galaxies may be pulled apart entirely by the gravity of larger neighbours. Their stars scatter along elongated paths, eventually becoming part of the larger galaxy's halo. Each such event leaves behind subtle signatures that astronomers can detect when mapping the motions and compositions of stars across a galaxy. Through careful observation of these clues, scientists can reconstruct the past interactions that shaped a galaxy's current form. In this sense, every galaxy carries a kind of memory. Its shape, its stellar populations, and the motion of its stars all record the events that have influenced it over billions of years. Spiral arms suggest a history rich in gas and star formation. Smooth elliptical structures hint at ancient mergers and long periods of quiet evolution. Irregular shapes reveal the gravitational tug of neighbouring galaxies. Even the smallest dwarf systems preserve evidence of how matter gathered in the early universe. The galaxies we observe today therefore represent not just objects in space, but ongoing stories. Their forms are temporary arrangements of matter shaped by gravity, time, and the environment surrounding them. Over the immense span of cosmic history, these structures continue to change, merge, grow, and sometimes fade. And when we observe distant galaxies whose light began travelling billions of years ago, we are seeing earlier chapters of those same stories unfolding across the universe. Over immense stretches of time, the universe rarely appears hurried. Galaxies drift through space with a calmness that makes their movement seem almost motionless when measured against the length of a human life. Even the fastest stars inside a galaxy require hundreds of millions of years to complete a single orbit around the galactic centre. From our perspective, the cosmos seems steady and unchanging, but on the deeper timescales of the universe, motion is everywhere. Galaxies are not anchored in place. They move through the cosmic web, guided by the same invisible gravitational structures that helped create them in the first place. And sometimes, after drifting for billions of years across intergalactic space, two galaxies meet. When that happens, the quiet architecture of the universe briefly becomes something far more dramatic. A galaxy collision is not like a car crash or an explosion. It unfolds slowly, often taking hundreds of millions or even billions of years to complete. But the consequences are enormous. Entire systems of stars are reshaped by gravity. Streams of light stretch outward across space, and new waves of star formation ignite inside clouds of compressed gas. To understand why galaxies collide at all, it helps to remember that the universe is not empty between them. Galaxies tend to gather in groups and clusters, bound together by gravity within the larger filaments of the cosmic web. The Milky Way itself belongs to a small collection of galaxies known as the local group. Within this group, dozens of galaxies move through space, slowly responding to one another's gravitational pull. Most of them are small dwarf galaxies orbiting the two largest members of the group, the Milky Way and the Andromeda Galaxy. Over billions of years, gravity subtly changes their paths. Galaxies may pass close to one another, exchanging streams of stars and gas, or in some cases merging entirely. These interactions have been happening since the earliest epochs of galaxy formation. In fact, many astronomers now believe that collisions and mergers played a major role in shaping the galaxies we see today. Yet despite the enormous number of stars inside a galaxy, direct collisions between individual stars during a galaxy merger are surprisingly rare. The reason is simple scale. Even though galaxies contain billions of stars, the distance between those stars is so vast that most of them pass by one another without ever coming close enough to interact directly. If the Sun were shrunk to the size of a small marble and placed at the centre of a large city, the nearest neighbouring stars would still be kilometres away. When two galaxies pass through each other, the stars behave like particles in a very sparse cloud, drifting through the encounter almost untouched. Instead, it is gravity that does most of the work. As galaxies approach each other, their gravitational fields begin to distort their shapes. Stars are pulled into new orbits, and long tidal tails of starlight may stretch outward into space. These tidal tails can extend for hundreds of thousands of light years, delicate arcs of stars tracing the complex gravitational dance between the merging galaxies. Gas clouds within the galaxies respond even more dramatically. When large reservoirs of gas collide, the clouds compress and heat, triggering intense bursts of star formation. Astronomers call these events starbursts. During a starburst phase, galaxies may produce new stars at rates dozens or even hundreds of times faster than normal. Entire clusters of bright blue stars ignite almost simultaneously, flooding the galaxy with ultraviolet radiation. The effect can transform the appearance of the galaxy for millions of years. Some of the most striking images captured by modern telescopes show galaxies caught in the midst of such collisions. The antennae galaxies, located about 60 million light-years away, provide one famous example. In photographs, they appear as two tangled, spiral systems whose arms have been stretched into long, curving streams resembling insect antennae. Within their overlapping disks, enormous regions of star formation glow brightly, marking places where gas clouds have been compressed by the collision. Another well-known example is the galaxy known as the Tadpole Galaxy. A long trail of stars stretches behind it like the tail of a comet, evidence of a past encounter that gravitationally pulled part of the galaxy outward into space. These structures may persist for hundreds of millions of years before gradually dispersing. Even our own galaxy carries signs of past interactions. Astronomers studying the outer regions of the Milky Way have discovered faint streams of stars moving together along elongated paths. These streams are thought to be the remnants of smaller galaxies that ventured too close and were gradually torn apart by the Milky Way's gravity. Over time, their stars became part of our galaxy's halo, quietly blending into its larger population. Such events remind us that galaxies grow not only by forming new stars, but also by absorbing smaller neighbours. The Milky Way has likely consumed many dwarf galaxies during its long history, and that process continues even today. One small satellite known as the Sagittarius Dwarf Galaxy is currently being stretched apart as it orbits our galaxy, leaving behind a trail of stars that wraps around the Milky Way like a faint ribbon. On even larger scales, entire spiral galaxies may merge together to create new systems. Computer simulations show that when two spiral galaxies of similar size collide, their orderly rotating disks can be disrupted completely. Stars are scattered into new orbits, and the combined system gradually settles into a more rounded shape. This process is one of the leading explanations for the formation of many elliptical galaxies. What begins as a pair of graceful spirals may eventually become a single massive elliptical galaxy after billions of years of gravitational interaction. While these events unfold slowly, they can dramatically reshape the galaxies involved. Streams of stars may be flung far into intergalactic space, forming diffuse halos that surround the merged system. Gas clouds may collapse in massive bursts of star formation before eventually being exhausted or blown away by energetic stellar winds and supernova explosions. In some cases, the central supermassive black holes of the merging galaxies may spiral toward each other and eventually combine, releasing enormous amounts of energy in the form of gravitational waves. These waves ripple through the fabric of space itself, traveling across the universe long after the galaxies have finished merging. The idea that galaxies collide might sound remote and abstract, but there is one particular collision that astronomers know will eventually involve our own galaxy. The Andromeda Galaxy, the nearest large neighbour of the Milky Way, is moving toward us at a speed of roughly 110 kilometers per second. Over the next 4 to 5 billion years, the distance between the two galaxies will gradually shrink. Eventually, their outer halos will begin interacting, and the first close pass will occur. From the perspective of any future observers living within the Milky Way, the night sky would change slowly but dramatically over millions of years. Andromeda would grow larger and brighter, eventually stretching across a significant portion of the sky. Its spiral arms would become visible as vast glowing structures arching through the darkness. As the two galaxies pass through each other, tidal streams of stars would form enormous arcs across space. New waves of star formation might ignite as gas clouds collide and compress. Yet despite the scale of this encounter, the vast distances between stars mean that the solar system itself would almost certainly survive the merger without any direct stellar collisions. Instead, our star would simply follow a new orbit within the combined galaxy that emerges from the event. Astronomers sometimes refer to the future merged system as Milkomeda, a blend of the names Milky Way and Andromeda. Over time, the chaotic structure created by the collision would gradually settle, likely forming a large elliptical galaxy containing the stars of both original systems. By the time this transformation is complete, the Sun itself may be approaching the end of its life as a star, and the appearance of the night sky would be entirely different from the one we see today. When we look outward into the universe now, observing distant galaxies whose light has travelled billions of years to reach us, we're often seeing other systems caught in these same dramatic moments of interaction. The graceful shapes of galaxies can change profoundly when gravity draws them together. What begins as two separate islands of stars may eventually become a single larger system, reshaped by the slow but powerful influence of gravity across cosmic time. When astronomers first began studying the centers of galaxies carefully, they expected to find dense clusters of stars, perhaps regions where gravity had gathered matter into especially crowded environments. What they discovered instead was something far stranger. At the heart of nearly every large galaxy lies an object so extreme that it reshapes the behavior of everything around it. These objects are not stars, not clusters, and not ordinary structures of matter. They are supermassive black holes, gravitational wells so powerful that once something crosses their boundary, not even light can escape. For many years, the idea seemed almost unbelievable. Black holes themselves were once considered little more than mathematical curiosities predicted by Einstein's theory of general relativity. Yet as telescopes improved and astronomers began measuring the motion of stars in galactic centers, the evidence grew impossible to ignore. The stars near the centers of galaxies were moving at astonishing speeds, sometimes thousands of kilometers per second, tracing tight orbits around something extremely massive and extremely compact. In our own galaxy, the evidence came from a region hidden deep within the constellation Sagittarius. The center of the Milky Way lies about 26,000 light-years away, buried behind thick clouds of dust that block visible light. For centuries, this region remained mysterious simply because telescopes could not see through the dust. Only with the development of infrared astronomy were scientists finally able to observe the stars near the galactic core. What they found was extraordinary. Using powerful telescopes in places like the Atacama Desert and the mountains of Hawaii, astronomers tracked the motion of individual stars orbiting the center of the Milky Way. Over years of careful observation, those stars traced looping paths through space, accelerating dramatically as they swung close to the center before racing outward again. Mapping these orbits precisely, scientists could calculate the mass of the object controlling them. The result was astonishing. The stars were orbiting an object containing roughly 4 million times the mass of our Sun, packed into a region no larger than our solar system. No known cluster of stars or other normal object could account for such density. The only explanation that fit the observations was a supermassive black hole. Astronomers named this hidden object Sagittarius A star, pronounced Sagittarius A star. Although the black hole itself cannot be seen directly, its presence is unmistakable. The stars around it behave exactly as predicted by the laws of gravity when influenced by such a massive compact object. Some of those stars complete full orbits in only a few decades, allowing astronomers to watch the dance of gravity unfold within a single human lifetime. Yet Sagittarius A star is actually a relatively quiet example of a supermassive black hole. In many other galaxies, these objects are far more active, producing phenomena so energetic that they can outshine the combined light of billions of stars. When large amounts of gas fall toward a black hole, they do not plunge directly into it. Instead, the gas begins swirling around the black hole, forming a rapidly spinning structure known as an accretion disk. As the gas spirals inward, it becomes compressed and heated by friction and gravitational forces. Temperatures within the disk can rise to millions of degrees, causing the material to emit intense radiation across many wavelengths of light. In this state, the region around the black hole can become one of the brightest objects in the universe. These brilliant centers of galaxies are known as quasars. The first quasars were discovered in the 1960s, when astronomers noticed extremely bright radio sources located far beyond our galaxy. At first, their true nature was confusing because they appeared star-like in telescope images, yet produced enormous amounts of energy. Eventually, scientists realized that these objects were the glowing cores of distant galaxies whose central black holes were actively consuming vast quantities of gas. Some quasars shine with the energy output of trillions of suns, making them visible across billions of light-years of space. the black hole itself does not emit this light. Instead, it is the surrounding accretion disk that produces the brilliance, as in falling matter, releases gravitational energy before disappearing beyond the event horizon. The process is astonishingly efficient. When matter falls into a black hole through an accretion disk, a significant portion of its mass can be converted into energy, far more efficiently than nuclear fusion inside stars. But the spectacle does not end there. In many cases, the rotating magnetic fields around the accretion disk channel some of the incoming energy into narrow beams that shoot outward from the poles of the black hole. These beams form enormous jets of charged particles traveling at speeds close to the speed of light. Known as relativistic jets, they can extend far beyond the host galaxy, sometimes stretching for hundreds of thousands of light years into intergalactic space. These jets are so powerful that they influence the environment of entire galaxy clusters, heating surrounding gas and shaping the flow of matter across enormous distances. For a long time, astronomers wondered whether these energetic phenomena were rare exceptions. But as more galaxies were observed, the pattern became clear. Almost every large galaxy examined closely appeared to contain a supermassive black hole at its center. Even galaxies that show no obvious signs of activity often reveal the quiet presence of a massive black hole when scientists measure the motion of nearby stars. The masses of these black holes vary widely. Some contain only a few million times the mass of the Sun, like Sagittarius A star. Others grow to truly enormous scales. The largest known examples exceed tens of billions of solar masses, making them among the most massive single objects in the universe. Even more intriguing is the discovery that the mass of a galaxy's central black hole is closely related to the properties of the galaxy itself. Galaxies with larger central bulges tend to host more massive black holes. This relationship suggests that galaxies and their central black holes evolved together over cosmic time, each influencing the growth of the other. One possibility is that black holes regulate star formation within their galaxies. When large amounts of gas fall toward a black hole and power an active galactic nucleus, the resulting radiation and jets can heat or expel surrounding gas. This process may limit how much gas remains available to form new stars, effectively controlling the galaxy's growth. In this way, the black hole becomes more than just a passive object at the center of a galaxy. It acts as a kind of cosmic engine influencing the evolution of the entire system. Although black holes themselves are regions from which nothing escapes, their presence shapes the fate of matter on scales far larger than their event horizons. Even galaxies that appear calm today may have experienced violent active phases in the past when their central black holes consumed large quantities of gas. Evidence of these past events sometimes remains in the form of giant bubbles of energized gas extending above and below the galactic plane. In our own Milky Way, astronomers have discovered such structures. Known as the Fermi bubbles, they extend tens of thousands of light years above and below the galaxy's center, glowing faintly in gamma rays. Many scientists believe they are the remnants of an ancient outburst from Sagittarius A star that occurred millions of years ago when the black hole briefly consumed a surge of infalling gas. Today, Sagittarius A star appears relatively quiet, but the presence of these enormous bubbles hints that the center of our galaxy was once far more energetic. Similar evidence appears in other galaxies, where central black holes periodically flare into activity before settling again into quieter states. In the broader story of galaxy evolution, these cycles of activity may play an important role in shaping the long-term structure of galaxies. The same black holes that once seemed like isolated cosmic oddities are now recognized as fundamental components of galactic architecture. They sit quietly at the centres of galaxies, often hidden from view, yet their gravitational and energetic influence extends far beyond their immediate surroundings. In some distant galaxies, they blaze so brightly that their light travels across billions of years of cosmic history to reach our telescopes. And even in quieter systems like the Milky Way, the subtle motion of stars around the galactic core reveals the presence of these extraordinary objects waiting silently at the heart of the galaxy. By the time astronomers began surveying large numbers of galaxies across the universe, a pattern seemed to emerge. Many galaxies fell into familiar categories: spirals with graceful arms rotating around bright centers, smooth elliptical systems filled mostly with older stars, smaller irregular galaxies whose shapes had been disturbed by gravitational encounters. At first glance, the universe appeared to follow a kind of quiet order, but as telescopes grew more powerful and observations reached deeper into space, something else became clear. The universe is not always orderly. In fact, some of the galaxies discovered over the past several decades look so unusual that they challenge the very definitions astronomers once used to classify them. These galaxies seem to break the rules, displaying shapes and behaviors that reveal just how creative gravity can be when matter interacts across billions of years. One of the most striking examples is the Ring Galaxy. Instead of the familiar spiral, structure, or smooth elliptical glow, ring galaxies appear as luminous circles of stars surrounding an empty center. At first glance, they resemble cosmic donuts floating in space. The Cartwheel Galaxy is perhaps the most famous example. Located about 500 million light-years away in the constellation Sculptor, it looks almost surreal in telescope images. A bright ring of star-forming regions surrounds a darker central region, while faint spokes of stars stretch inward like the ribs of a wheel. For years, astronomers wondered how such an unusual shape could form. The explanation appears to lie in an extraordinary kind of galactic collision. Imagine a smaller galaxy plunging directly through the center of a larger spiral galaxy. The gravitational shock of that passage sends a wave of compression outward through the larger galaxy's disk. Gas clouds become squeezed as the wave travels outward, triggering bursts of star formation along a growing circular front. The result is a luminous expanding ring of young stars racing away from the galaxy's center. Over time, that ring may slowly fade and disperse as the galaxy settles back into a more conventional shape. But for millions of years, the structure remains visible as one of the most unusual forms in the universe. Not all strange galaxies owe their appearance to collisions. Some challenge expectations simply by how little they seem to contain. In recent years, astronomers have discovered a class of objects known as ultra-diffuse galaxies. These galaxies are enormous in size, sometimes nearly as large as the Milky Way, yet they contain surprisingly few stars. When viewed through a telescope, they appear faint and ghostly, as though the galaxy itself were only barely there. One such object, known as Dragonfly 44, lies in the Coma Cluster about 300 million light-years away. Despite having a diameter comparable to the Milky Way, it contains only a tiny fraction of the stars found in our galaxy. Instead of hundreds of billions of suns, it holds perhaps only a few billion. Yet measurements of the motion of its stars suggest that the galaxy is still embedded within a massive halo of dark matter. In other words, Dragonfly 44 seems to be a galaxy that somehow formed the gravitational structure necessary for a large galaxy, but never converted much of its gas into stars. It is almost as though the universe began building a galaxy and then stopped halfway through the process. Discoveries like these reveal how much variety exists in the cosmic landscape. Some galaxies blaze with intense activity, while others remain quiet and sparse. In fact, certain galaxies are so active that they produce new stars at astonishing speeds. These are known as starburst galaxies. In a typical spiral galaxy like the Milky Way, only a few new stars form each year. That may sound impressive, but in starburst galaxies the rate can increase dramatically. Dozens or even hundreds of stars may ignite annually, flooding the galaxy with brilliant young clusters and intense radiation. One famous example is the galaxy Messier 82, often called the Cigar Galaxy. Located about 12 million light-years away, it appears relatively ordinary at first glance. But when astronomers observe it in infrared and radio wavelengths, the center of the galaxy reveals extraordinary activity. Gas clouds are collapsing rapidly, forming new stars at a pace far beyond that seen in calmer galaxies. The intense radiation and stellar winds from these newborn stars push gas outward in enormous plumes that extend thousands of light-years above and below the galaxy's disk. These outflows resemble gigantic fountains of glowing gas, carrying material away from the galaxy's core. Starburst phases like this often occur when galaxies interact with nearby neighbors. Gravitational disturbances compress gas clouds, triggering sudden waves of star formation that may last for tens of millions of years before gradually fading. During these episodes, galaxies can become some of the brightest objects in the universe, briefly transforming themselves into cosmic furnaces where stars ignite in rapid succession. Yet the opposite extreme also exists. Some galaxies appear to have almost no stars at all. These rare objects are sometimes referred to as dark galaxies. Unlike normal galaxies, which shine brightly with billions of stars, dark galaxies consist mostly of gas and dark matter with little visible starlight. Detecting them is extremely difficult because there are few luminous objects to reveal their presence. In many cases, astronomers infer their existence indirectly by observing how gas moves in regions where gravity seems stronger than visible matter alone can explain. One candidate for such a system is a cloud of hydrogen gas known as VIRGOHI21. Located in the Virgo cluster, it appears to contain a large amount of mass despite showing almost no evidence of stars. If confirmed as a true dark galaxy, it would represent a system where matter gathered into a galactic structure, but somehow failed to ignite the star formation that normally makes galaxies visible. The existence of such objects raises fascinating questions about the conditions required for galaxies to produce stars. Perhaps certain environments prevent gas from cooling efficiently. Perhaps energetic events in the past expelled the gas before star formation could begin. Or perhaps some galaxies simply follow unusual evolutionary paths shaped by their surroundings. Even among galaxies that do form stars, the patterns can vary dramatically. Some distant galaxies discovered by modern telescopes appear to be forming stars at rates hundreds of times greater than the Milky Way. These galaxies, sometimes called hyperstarburst systems, convert enormous quantities of gas into stars within relatively short periods of cosmic time. Observations from telescopes like the Atacama Large Millimeter Array in Chile reveal dense regions of gas, collapsing rapidly under gravity. Within these regions, entire clusters of stars ignite almost simultaneously, producing intense bursts of light and radiation. Over time, such rapid star formation may exhaust the galaxy's gas supply, leaving behind a system filled mostly with older stars and little remaining material for future generations. These unusual galaxies remind astronomers that the universe does not follow a single blueprint for how galaxies should behave. Some galaxies grow slowly and steadily over billions of years. others experience dramatic bursts of activity triggered by collisions or internal instabilities. Some remain faint and diffuse, while others blaze with extraordinary brightness as new stars ignite in rapid succession. And occasionally the universe produces shapes so unusual that they seem almost artistic. Rings of light or ghostly clouds of stars drifting across space. Each of these systems represents a different experiment carried out by gravity and matter over cosmic time. When astronomers observe them, they're not simply cataloguing oddities. They're witnessing the immense range of possibilities that emerge when the ingredients of the universe interact under the influence of gravity, time, and the invisible structures that guide the formation of galaxies across the cosmos. If galaxies are vast ecosystems of stars and gas drifting through space, the next mystery becomes unavoidable. What is actually holding them together? When astronomers first began measuring the motion of stars inside galaxies in detail, the results were quietly unsettling. These stars were moving far too fast. To understand why this mattered, imagine watching a small object orbiting something much larger. A planet circles a star because gravity pulls it inward, while its motion carries it forward. The balance between these two influences determines how quickly the planet must travel. The farther it is from the central star, the weaker the gravitational pull becomes, and the slower the orbit should be. This simple relationship works beautifully within our solar system. Mercury races around the Sun in just 88 days, while distant Neptune takes more than a century to complete one orbit. Distance weakens gravity, and motion slows accordingly. Astronomers expected galaxies to behave in the same way. The stars near a galaxy's center should move quickly, pulled strongly by the combined gravity of the stars packed into that region. Farther out, where the visible stars grow sparse, the gravitational grip should weaken, and the outer stars should drift along more slowly. But when scientists carefully measured the speeds of those distant stars, they found something different. Instead of slowing down, the stars at the outer edges of galaxies were moving almost as quickly as those much closer to the center. In some cases, they were traveling so fast that, according to the visible mass of the galaxy, they should have escaped entirely and flown off into intergalactic space. Yet they did not. They remained bound to the galaxy, continuing their long, slow orbits as though an enormous invisible weight were holding everything together. This discovery emerged gradually throughout the 20th century, but it was the work of astronomer Vera Rubin in the 1970s that brought the evidence into sharp focus. Rubin studied the rotation of spiral galaxies with remarkable precision, mapping how fast stars were moving at different distances from the galactic center. The patterns she found were impossible to ignore. The rotational speed of galaxies remained almost constant far beyond the regions where most visible stars and gas existed. It was as though the galaxy were embedded inside a much larger unseen structure whose gravity dominated the system. This hidden component came to be known as dark matter. The name itself is simple, almost understated. Dark because it does not emit or reflect light in ways our telescopes can detect. Matter because its gravitational influence behaves exactly as mass should. Whatever dark matter is made of, it interacts with the universe primarily through gravity. It does not form stars or planets, and it does not glow. Yet its presence can be traced by the way galaxies move and bend light around them. One of the most powerful pieces of evidence comes from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of space itself. Light traveling near such objects follows curved paths, bending as it passes through the distorted geometry around them. When astronomers observe distant galaxies through the gravitational influence of a massive foreground galaxy or cluster, the background light becomes stretched, magnified, or even duplicated into arcs and rings. By carefully measuring these distortions, scientists can map how mass is distributed within the foreground object. Again and again, these maps reveal far more mass than can be explained by visible matter alone. Vast halos of unseen mass surround galaxies and galaxy clusters, extending far beyond the regions where stars are found. In many cases, the dark matter halo contains several times more mass than the luminous galaxy embedded within it. It is as though the stars we see are only the bright center of a much larger invisible structure. Once astronomers began accounting for this hidden mass, the behavior of galaxies suddenly made sense. The stars are not flying apart because they are orbiting inside enormous halos of dark matter whose gravity extends far beyond the visible disk. But the implications of dark matter reach even further. When scientists simulate the formation of galaxies in computer models of the early universe, something fascinating appears. In the aftermath of the Big Bang, matter was not perfectly evenly distributed. Tiny fluctuations in density existed, regions where slightly more matter gathered than in neighbouring areas. Over time, gravity amplified those small differences. Matter slowly flowed toward denser regions, building larger structures. But ordinary matter alone, the atoms that form stars and gas clouds, would have struggled to assemble galaxies quickly enough to match what we observe today. Dark matter changes that story completely. Because it interacts only weakly with radiation, dark matter began clumping together long before ordinary matter could cool and collapse. These early dark matter concentrations acted like gravitational seeds. Gas gradually fell into their invisible wells, cooling and condensing until the first stars ignited. In this picture, dark matter forms the scaffolding upon which galaxies are built. The visible structures we admire in telescope images are only the luminous highlights tracing out a deeper invisible architecture. As computer simulations improved and observational surveys expanded, astronomers began noticing that galaxies themselves are not randomly scattered throughout the universe. Instead, they follow a striking pattern. When mapped across enormous distances, galaxies arrange themselves along long filaments that stretch for hundreds of millions of light years. These filaments intersect at dense nodes where massive clusters of galaxies reside. Between them lie vast empty regions, called cosmic voids, where very few galaxies exist at all. The resulting structure resembles a vast web. Delicate threads of galaxies span the universe, surrounding enormous cavities that appear almost completely empty. This pattern is now known as the cosmic web. It is one of the largest structures known to exist, stretching across the observable universe in a network of filaments and clusters. When astronomers compare observations of this web to simulations of dark matter in the early universe, the resemblance is striking. The same filaments appear in both. The same nodes of dense structure emerge where multiple strands intersect. The galaxies themselves seem to follow the underlying distribution of dark matter almost perfectly, tracing its invisible shape across cosmic distances. In this sense, the universe has a kind of hidden skeleton. Dark matter forms the framework, and galaxies illuminate it like tiny lanterns strung along its threads. Without that framework, the universe would likely look very different. Galaxies might have formed much later, or perhaps not at all. The delicate structures we see today might never have had time to assemble before cosmic expansion carried matter too far apart. Even now, scientists do not yet know exactly what dark matter is made of. Many theories propose new kinds of particles that interact weakly with ordinary matter. Experiments deep underground attempt to detect these particles directly as they pass through detectors shielded from cosmic radiation. Others search for indirect signals in space, hoping that dark matter particles might occasionally collide and produce detectable radiation. So far, the results remain inconclusive. The nature of dark matter continues to be one of the greatest unsolved questions in physics, yet its gravitational influence is unmistakable. Every galaxy we observe appears embedded within its invisible halo. Every cluster of galaxies shows evidence of enormous hidden mass binding it together. Even the overall pattern of cosmic structure across billions of light years reflects the distribution of dark matter in the early universe. When we step back and consider the full picture, the familiar luminous universe begins to look almost like a surface phenomenon. The stars, nebulae, and galaxies that fill astronomical photographs represent only a small fraction of what is actually there. Beneath that glowing layer lies a far larger network of unseen matter, quietly shaping everything we observe. Galaxies drift along the filaments of this structure like beads sliding along invisible threads. Over billions of years, gravity pulls them together, guiding their motions in ways that only become apparent when we observe the universe at its largest scales. And when we look deep into space, we're not only seeing distant galaxies shining across the darkness, we're glimpsing the faint outline of the cosmic web itself, illuminated by the galaxies that formed along its hidden pathways. When astronomers first began identifying galaxies beyond the Milky Way, the discovery alone was enough to completely transform humanity's understanding of the universe. But as telescopes improved and sky surveys expanded, something else gradually became clear. Galaxies themselves are not scattered randomly through space like grains of sand thrown across a floor. Instead, they gather together, following patterns shaped by gravity and the invisible structures of dark matter. What at first looked like an immense cosmic emptiness slowly revealed a far more intricate design. Galaxies prefer company. Many of them live in groups, clusters, and enormous networks that stretch across the observable universe. One of the simplest examples is the kind of neighborhood our own galaxy inhabits. The Milky Way belongs to a modest collection known as the local group. Within this region of space, more than 50 galaxies drift together under their mutual gravitational influence. Most of them are small, dwarf galaxies, quiet systems containing only a few million or a few billion stars. They orbit around the two dominant members of the group, the Milky Way and the Andromeda Galaxy. These smaller companions move slowly through space, tracing elongated paths as gravity binds the group together. Occasionally they wander too close to one of the larger galaxies and are gradually torn apart, their stars stretched into long streams that wrap around the halo of the larger system. Yet the local group is only a small example of something much larger. Beyond it lie galaxy clusters, enormous collections containing hundreds or even thousands of galaxies bound together by gravity. Within these clusters, the distances between galaxies shrink compared to the emptier regions of space. Galaxies drift through the cluster environment, sometimes interacting, sometimes merging, sometimes passing by one another in long, gravitational encounters that reshape their structures. One of the best-known examples is the Virgo cluster, located roughly 55 million light-years away. This cluster contains more than 1,000 galaxies, including giant elliptical systems that dominate the cluster's central regions. The galaxies inside Virgo move through a vast cloud of extremely hot gas that fills the space between them. This gas is so energetic that it emits powerful X-rays, revealing the cluster's presence even when individual galaxies are difficult to observe. The gravitational pull of all that mass holds the cluster together, creating a region where galaxies live in close proximity for billions of years. On even larger scales, clusters themselves gather into still greater formations known as superclusters. These immense structures span hundreds of millions of light years and contain multiple galaxy clusters linked together by gravity. For many years, astronomers believed superclusters represented the largest structures in the universe. But even that view eventually expanded as surveys of distant galaxies revealed something even more extraordinary. When scientists mapped the positions of millions of galaxies across enormous volumes of space, they discovered that these galaxies formed an intricate pattern resembling a three-dimensional web. Long filaments of galaxies stretched across cosmic distances, intersecting at dense nodes where clusters gathered. Between these filaments lay enormous empty regions known as cosmic voids. Some of these voids are hundreds of millions of light years across and contain very few galaxies at all. The resulting structure looks almost organic when visualized, like a vast network of interconnected threads spanning the observable universe. Astronomers call this structure the cosmic web. The cosmic web is one of the most remarkable discoveries in modern cosmology. It reveals that the universe possesses a kind of large-scale architecture shaped by gravity and dark matter over billions of years. The filaments trace the regions where matter gathered most strongly after the Big Bang, while the voids represent areas where matter remained comparatively sparse. When astronomers compare observations of this cosmic web with computer simulations of the early universe, the similarities are striking. In simulations, dark matter collapses into filaments under the influence of gravity, creating a network of dense regions connected by long strands. Ordinary matter then falls into those same regions, forming galaxies along the dark matter scaffolding. In this way, the luminous galaxies we observe today trace the underlying distribution of dark matter throughout the universe. One of the most fascinating consequences of this structure is that galaxies often travel along the filaments of the cosmic web. Gravity slowly guides them toward the dense nodes where clusters reside. Over billions of years, this process funnels galaxies into larger and larger gatherings, gradually building the enormous structures we observe today. Our own galaxy participates in this cosmic flow. The Milky Way and its neighbouring galaxies are not isolated in space, but belong to a much larger structure known as the Laniakea supercluster. The name Laniakea comes from the Hawaiian language and roughly translates to immense heaven. It is a fitting description. This supercluster spans more than 500 million light-years and contains roughly 100,000 galaxies, including the Virgo cluster near its centre. Within this enormous region, galaxies drift slowly along gravitational pathways that ultimately lead toward a massive concentration of matter, sometimes called the Great Attractor. The Great Attractor itself is hidden behind dense clouds of dust within the plane of the Milky Way, making it difficult to observe directly. Yet its gravitational influence can be detected through the motions of galaxies across vast distances. Many galaxies within the Laniakea supercluster appear to be drifting gradually toward this unseen region, pulled along the filaments of the cosmic web. When astronomers visualize the flow of galaxies across this enormous structure, the pattern looks surprisingly familiar. It resembles the branching structure of a river system, where smaller streams merge into larger currents that eventually lead toward a central basin. Or, as some scientists have noted, it resembles the network of neurons within a brain. Filaments of galaxies extend outward like cosmic synapses, linking clusters across immense distances. The comparison is not perfect, of course. but it captures something important about the universe. On its largest scales, the cosmos displays patterns that are both intricate and surprisingly organized. Gravity has taken the simple ingredients of matter and dark matter and arranged them into a vast interconnected structure stretching across billions of light years. Yet even this grand architecture contains enormous emptiness. The cosmic voids that lie between the filaments are among the largest known regions of near emptiness in the universe. Within these voids, galaxies are extremely rare. If an observer lived inside one of these regions, the night sky would look dramatically different. Instead of the rich tapestry of galaxies visible from denser cosmic environments, the sky might contain only a few distant systems scattered faintly across the darkness. These voids are not completely empty. They still contain dark matter, small galaxies, and thin gas drifting through space. But compared to the dense filaments and clusters surrounding them, they are remarkably quiet regions of the cosmos. Over time, the expansion of the universe tends to make these voids grow larger as matter continues flowing toward the denser structures along the cosmic web. When astronomers step back and examine the universe at these enormous scales, individual galaxies begin to look almost insignificant. Each galaxy may contain hundreds of billions of stars, but within the cosmic web they appear as tiny points marking the intersections of far larger structures. Yet these points of light allow us to map the grand architecture of the universe itself. By observing where galaxies gather and where they are absent, scientists can trace the distribution of matter across billions of light years. In doing so, they reveal the immense network that gravity has been shaping since the earliest moments after the Big Bang. The galaxies we observe drifting along these filaments and gathering in clusters are not isolated islands after all. They are part of a far larger cosmic system, a network so vast that its full extent can only be glimpsed through the combined light of countless distant galaxies spread across the universe. As the universe continued evolving and galaxies assembled themselves through countless mergers and waves of star formation, not every system remained active forever. Many galaxies, especially in the earlier universe, were filled with bright regions where new stars were constantly being born. Massive clouds of hydrogen collapsed under gravity, igniting brilliant clusters that illuminated spiral arms and galactic disks. But over billions of years, something begins to change inside some galaxies. The raw materials needed to build new stars slowly run out. What was once a lively stellar nursery gradually becomes quieter. When astronomers observe galaxies across the universe, they notice that many of them appear bright blue. This colour comes from massive young stars that burn extremely hot and shine with intense blue-white light. These stars live fast and die young, often surviving only a few million years before ending their lives in powerful supernova explosions. Because their lifetimes are so short, their presence indicates that new stars must be forming continuously to replace them. Blue galaxies therefore tend to be active galaxies, places where gas clouds are still collapsing and new stars are being born. But not all galaxies share this youthful glow. Some appear much redder and softer in colour. These are often referred to as red galaxies, and their appearance tells a very different story. Instead of containing large numbers of young blue stars, they are dominated by older stars that shine with cooler reddish light. These stars may be billions of years old, long past the energetic youth that once defined them. When astronomers see a galaxy whose light is dominated by red stars, they often describe it informally as red and dead. The phrase may sound dramatic, but it captures something real about these systems. They are not literally dead, of course. Their stars still shine, orbiting the galactic center just as they always have, but the galaxy itself has largely stopped forming new stars. The processes that once turned gas clouds into brilliant young suns have slowed or ceased entirely. In many cases, this happens because the galaxy has exhausted its supply of cold gas. Star formation depends on the presence of dense molecular clouds, regions where hydrogen can collapse under gravity and ignite nuclear fusion. Over time, those clouds are gradually consumed as stars form. Stellar winds, radiation, and supernova explosions can also push gas out of the galaxy, or heat it so much that it can no longer collapse easily. Once the available gas is gone or too hot to condense, star formation begins to fade. The galaxy slowly transitions into a quieter phase of its life. Elliptical galaxies provide some of the most striking examples of this stage. Unlike spiral galaxies with their glowing arms of star formation, elliptical galaxies often contain little cold gas or dust. Their stellar populations are dominated by older stars that formed long ago during earlier epochs of galaxy assembly. These galaxies appear smooth and featureless in telescope images, their light evenly distributed without the bright knots and nebulae that mark active star-forming regions. Many of the largest galaxies in the universe fall into this category. In massive galaxy clusters, giant elliptical galaxies often sit near the center, like enormous stellar islands surrounded by smaller companions. These systems may have formed through a long history of mergers in which spiral galaxies collided and combined. During those violent interactions, gas clouds may have been compressed into intense starbursts that consumed much of the available fuel in relatively short periods of time. Once that fuel was gone, the galaxy settled into a calmer existence dominated by older stars. Some elliptical galaxies contain trillions of stars, far more than the Milky Way. Yet despite their enormous size, they often appear surprisingly quiet. Without large reservoirs of gas to form new stars, the galaxy gradually becomes a kind of stellar retirement community where ancient stars drift in vast orbits through a slowly evolving gravitational landscape. Astronomers can determine the ages of stars within these galaxies by studying their spectra. The light emitted by stars carries subtle fingerprints that reveal their chemical composition and approximate age. Observations of elliptical galaxies often show that many of their stars formed during the early epochs of the universe, perhaps 10 billion years ago or more. These stars have been shining ever since, gradually evolving as they consume the nuclear fuel in their cores. Over time, the most massive stars have already ended their lives in supernova explosions, leaving behind neutron stars or black holes. The stars that remain today are generally smaller and longer-lived, burning their fuel slowly across billions of years. This aging stellar population gives elliptical galaxies their characteristic reddish glow, but the quieting of star formation can happen in other ways as well. In dense galaxy clusters, galaxies sometimes lose their gas through interactions with the surrounding environment. As a galaxy moves through the hot gas that fills a cluster, pressure from that gas can strip away the galaxy's own gas clouds in a process known as ram pressure stripping. The galaxy effectively leaves a trail of gas behind it as it travels through the cluster, much like wind-blowing leaves off a moving vehicle. Without that gas, star formation inside the galaxy gradually slows and eventually stops. In other cases, the central supermassive black hole may play a role in shutting down star formation. When a black hole becomes active and begins consuming gas, the resulting energy output can heat surrounding gas or blow it away from the galaxy entirely. This feedback process may prevent fresh gas from cooling and collapsing into new stars. Over time, the galaxy's supply of star-forming material dwindles, leaving behind only the stars that formed during earlier phases of its history. Even spiral galaxies like the Milky Way may eventually experience this quieting process. Our galaxy still contains large clouds of gas where new stars are forming, but the rate of star formation has gradually declined compared to earlier periods in its history. Billions of years from now, as the available gas continues to be consumed or dispersed, the Milky Way may also become a calmer galaxy dominated by older stars. When astronomers look deep into the universe, they can see examples of galaxies at many different stages of this process. Some distant galaxies appear extremely active, blazing with star formation as gas collapses rapidly into new stellar systems. Others already appear quiet and mature, their light dominated by stars that formed long ago. These observations help scientists reconstruct the life cycles of galaxies across cosmic time. In this sense, galaxies have something resembling a life story. They begin as chaotic collections of gas and young stars forming in the early universe. Over time, they grow through mergers, bursts of star formation, and gradual accumulation of matter. Eventually, many of them settle into quieter states where star formation slows or stops, leaving behind vast populations of aging stars. The galaxies that appear red and quiet today are not failures of cosmic evolution. They're simply older systems that have moved beyond their most active periods. Their light carries the accumulated history of billions of years of stellar activity, even if that activity has now slowed to a gentle glow. When astronomers observe these ancient galaxies, they are looking at systems that have already lived through the dramatic phases of their evolution. What remains is the quiet radiance of stars that continue to shine long after the galaxy itself has stopped building new ones. As telescopes grew more powerful throughout the 20th century, astronomers gradually realized that looking farther into space also meant looking farther back in time. Every distant galaxy is seen not as it is today, but as it was when its light began traveling across the universe. That idea becomes even more profound when observations reach extreme distances, where the light we detect left its source billions of years ago. In those cases, we're not merely observing remote galaxies. We're witnessing the universe during its earlier stages, when galaxies themselves were still young, and the cosmic landscape looked very different from what we see nearby. One of the most remarkable demonstrations of this idea began in the mid-1990s with an experiment that seemed almost reckless at the time. Astronomers using the Hubble Space Telescope decided to point the telescope at what appeared to be an almost completely empty patch of sky. The region chosen was incredibly small, roughly the size of a grain of sand held at arm's length against the night sky. To the human eye, and even to most telescopes on Earth, the area seemed nearly blank, with very few visible stars and no obvious galaxies. For 10 days in December of 1995, Hubble stared at that tiny region without looking anywhere else. Instead of taking a quick photograph, the telescope gathered light continuously, accumulating faint signals from objects far too dim to appear in ordinary observations. As the exposures piled up, something extraordinary began to emerge from the darkness. When the final image was assembled, what had seemed like empty space was suddenly filled with galaxies, thousands of them. Tiny spirals, faint elliptical shapes, irregular patches of starlight, all crowded together within that minuscule field of view. The image became known as the Hubble Deep Field. It remains one of the most iconic astronomical photographs ever taken. The reason it was so shocking is that it revealed just how densely populated the universe is with galaxies. That tiny patch of sky contained objects spanning an enormous range of distances. Some were relatively nearby by cosmic standards, perhaps a few 100 million light-years away. Others were so distant that their light had begun travelling toward us billions of years before Earth even formed. The deeper astronomers looked into the image, the further back in time they were seeing. Each faint galaxy represented an earlier chapter in the history of the universe. Some of the most distant galaxies in the Hubble Deep Field existed when the universe was only a few billion years old. Their shapes often appeared smaller and more chaotic than the mature galaxies closer to us. Many lacked the elegant spiral arms seen in nearby systems. Instead, they looked irregular, as though gravity had only recently begun assembling them from smaller pieces. These observations supported the growing idea that galaxies evolved gradually over cosmic time. The earliest galaxies were small and turbulent, merging with neighbours and forming stars at rapid rates. As billions of years passed, these systems combined into larger structures and eventually settled into the more stable forms we see in the present universe. Encouraged by the success of the first deep field image, astronomers later repeated the experiment in other regions of the sky. Each time the results told the same story. What appeared empty at first glance was actually filled with distant galaxies whose light was simply too faint to detect in short exposures. With enough observing time, the darkness dissolved into a tapestry of ancient starlight. Yet even Hubble had limits. Although it could see extremely far into the universe, the most distant galaxies posed a particular challenge. Because the universe has been expanding since the Big Bang, light travelling across billions of years becomes stretched to longer wavelengths. Visible light from the earliest galaxies is shifted into the infrared part of the spectrum by the time it reaches us. Hubble was not optimised for observing these faint infrared signals. To push further back in time, astronomers needed a new kind of telescope designed specifically to detect that ancient stretched light. That telescope arrived in December of 2021 with the launch of the James Webb Space Telescope. Webb was built to observe the universe in infrared wavelengths, allowing it to detect the faint glow of galaxies whose light has been travelling for more than 13 billion years. Positioned far beyond Earth in a stable orbit nearly 1.5 million kilometers away, Webb unfolded its enormous gold-coated mirror and began collecting light from the deepest reaches of space. Almost immediately, the telescope began revealing galaxies that had never been seen before. Some of these galaxies appear so distant that their light began its journey when the universe was less than 5% of its current age. In terms of cosmic history, this means we're observing structures that formed only a few 100 million years after the Big Bang. That period represents the time when the very first galaxies were beginning to assemble from the primordial gas left behind by the early universe. Webb's images show faint clusters of galaxies emerging from the darkness, their light stretched and reddened by billions of years of cosmic expansion. Many of these galaxies are surprisingly bright and complex considering how young the universe was at that time. Some appear to contain significant populations of stars already, suggesting that galaxy formation began earlier and proceeded faster than many astronomers once expected. These discoveries are still reshaping our understanding of how the first galaxies formed. The early universe may have been far more efficient at building galaxies than earlier models predicted. Gas flowing along the filaments of the cosmic web may have collapsed rapidly into dense regions where star formation ignited on massive scales. Observing such distant galaxies is extraordinarily difficult. Their light is incredibly faint by the time it reaches Earth, and many of them appear only as tiny points even in Webb's powerful images. Yet each one carries information about the earliest chapters of cosmic history. By studying their brightness, colours, and spectral signatures, astronomers can estimate how many stars they contain, how quickly those stars are forming, and what chemical elements are present within them. In doing so, they are essentially reconstructing the conditions of the universe during its infancy. Every photon collected by telescopes like Hubble and Webb is a messenger from the past, carrying evidence of what the universe looked like long before our galaxy existed. When we observe galaxies whose light has travelled for 13 billion years, we are seeing objects that formed shortly after the first stars ignited. The atoms inside our own bodies were created much later, inside generations of stars that lived and died over billions of years. Yet by studying these distant galaxies, we can trace the sequence of events that eventually led to the formation of the Milky Way, the Sun, and the small planet where we now sit observing the cosmos. In this sense, the deepest galaxies humans have ever seen are not merely distant objects scattered across space. They are ancient witnesses to the moment when the universe first began assembling the complex structures that would eventually fill it with galaxies, stars, planets, and perhaps even life. When astronomers observe distant galaxies, they are almost always looking backward in time. The light from those galaxies began its journey billions of years ago, long before the modern universe took its current shape. But once we understand how galaxies formed and evolved, it becomes possible to imagine something equally fascinating. We can begin to look forward. The same laws of gravity and physics that shaped galaxies in the past will continue shaping them in the future. And while the changes unfold across timescales far longer than any human civilization could ever witness, the broad outline of that future is something astronomers can already glimpse. Galaxies, like living systems, pass through different phases of existence. They are born in the early universe when gas collapses into the first stars. They grow through mergers and bursts of star formation. They settle into mature structures filled with billions of suns orbiting slowly through space. But eventually even galaxies begin to age. The processes that once fueled their activity gradually fade. The supply of cold gas that feeds star formation becomes scarcer. The bright blue stars that once illuminated their spiral arms burn out and disappear. What remains is a quieter, slower system, filled mostly with older stars whose light glows with a soft reddish hue. One of the most important forces shaping the future of galaxies will be gravity itself. Even though the universe is expanding, galaxies within the same gravitational neighborhoods remain bound together. Groups and clusters of galaxies will continue interacting, and over billions of years many of them will merge into larger systems. We've already seen how such mergers shape galaxies today. Spiral galaxies collide and combine, forming larger elliptical systems. Smaller dwarf galaxies are absorbed by their larger neighbors. These processes will continue far into the future. Within the local group, one of the most dramatic events yet to occur involves the two largest galaxies in our neighborhood. The Milky Way and the Andromeda Galaxy are slowly moving toward each other. Their current separation is about 2.5 million light-years, but gravity is steadily pulling them closer together. Measurements of Andromeda's motion show that it is approaching the Milky Way at roughly 110 kilometers per second. At that speed, the distance between the two galaxies will gradually shrink over the next several billion years. In roughly 4 to 5 billion years, the first close encounter between the two galaxies is expected to occur. For any observers who might exist in the distant future, the night sky would slowly change over millions of years. The Andromeda Galaxy, which now appears as a faint smudge in our sky, would grow steadily larger and brighter. Eventually it would stretch across a large portion of the heavens, its spiral arms glowing like enormous rivers of starlight. As the two galaxies begin their gravitational dance, tidal forces will distort their shapes. Long streams of stars will stretch outward into space, tracing the invisible currents of gravity pulling both galaxies into new forms. Gas clouds will collide and compress, igniting bursts of star formation throughout both systems. Yet even during such a dramatic event, the vast distances between stars mean that individual stellar collisions will remain extremely rare. Most stars will simply pass one another by, their paths altered by gravity but never coming close enough to collide. Over time, the two galaxies will continue interacting, passing through each other more than once before finally settling into a single merged system. Astronomers sometimes refer to this future galaxy informally as Milkomeda, a blend of the names Milky Way and Andromeda. The final structure will likely resemble a large elliptical galaxy, with the orderly spiral patterns of both original galaxies replaced by a more rounded distribution of stars. By the time this transformation is complete, the Sun itself may already be nearing the end of its life as a star. But galaxy mergers alone do not define the long-term future of galaxies. Another crucial factor is the gradual decline of star formation. The universe began with vast supplies of hydrogen gas, the raw material needed to build stars. Over billions of years, that gas has steadily been converted into stars and heavier elements. Some gas remains within galaxies today, but the overall supply has been diminishing. As time passes, galaxies will find it increasingly difficult to form new stars. Eventually, many galaxies will enter a stage where star formation becomes extremely rare. Their existing stars will continue shining, but the creation of new ones will slow to a near halt. In these aging galaxies, the stellar population will become dominated by long-lived stars like red dwarfs. These small stars burn their fuel very slowly and can survive for trillions of years, while massive stars explode in supernovae after only a few million years. Red dwarfs can shine quietly for periods far longer than the current age of the universe. In the far future, many galaxies will therefore appear faint and reddish, illuminated primarily by these long-lived stars. At the centers of galaxies, another process will continue unfolding quietly. The supermassive black holes that reside there will keep growing. Whenever gas or stars drift too close to the galactic center, they may be pulled inward and eventually consumed by the black hole. During galaxy mergers, the central black holes of the merging systems may spiral together and eventually combine, forming even larger black holes. When two such massive objects merge, they release enormous bursts of gravitational waves that ripple outward across space. These waves carry energy away from the merging system, subtly altering the structure of space-time itself as they travel across the universe. Over billions and trillions of years, supermassive black holes may gradually grow larger as they absorb matter from their surroundings. Yet even these enormous objects cannot escape the long-term changes occurring throughout the universe. As star formation declines and galaxies consume or lose their remaining gas, the luminous activity within them will slowly fade. The universe itself is also expanding at an accelerating rate due to dark energy. Over extremely long timescales, this expansion will carry distant galaxies farther and farther away from one another. Eventually, galaxies outside our local gravitational neighborhood may drift beyond the observable horizon entirely. Future observers living within the merged Milky Way and Andromeda galaxy might look into the sky and see far fewer galaxies than we do today. The vast cosmic web we observe now could gradually disappear from view as expansion stretches space itself beyond the reach of light traveling between distant systems. Within individual galaxies, however, the quiet glow of stars will persist for unimaginable lengths of time. Red dwarfs will continue burning slowly. White dwarf remnants of older stars will cool gradually over trillions of years. occasional stellar interactions may still occur, and black holes will remain at the centers of galaxies, silently anchoring the motion of the surrounding stars. In this far future, the universe will not suddenly end in a dramatic event. Instead, it will slowly grow quieter. The brilliant epochs of star formation that once filled galaxies with glowing nebulae and young clusters will fade into memory. What remains will be the long afterglow of countless stars continuing their patient orbits through galaxies that have grown old along with the universe itself, after travelling across billions of years of cosmic history, after tracing the birth of the first galaxies, the violent collisions that reshape them, the hidden black holes at their centres, and the enormous structures that weave them together across the universe. The story inevitably returns to a quieter and more reflective question. Why do we look at all of this in the first place? Galaxies exist whether anyone observes them or not. They drift through space guided by gravity, forming stars, colliding with neighbours, and evolving across spans of time so vast that the entire history of humanity occupies only a tiny fraction of their lives. Yet on one small planet orbiting an ordinary star, a species emerged that learned how to wonder about these distant structures. Long before telescopes or satellites existed, people looked up at the night sky and tried to understand what they were seeing. To ancient observers, the sky was not an empty backdrop, but a place filled with stories, patterns, and meaning. Constellations were drawn between the stars, forming shapes of animals, heroes, and mythological creatures. These patterns helped early civilizations navigate, measure the passage of seasons, and organize calendars that guided agriculture and daily life. Even without knowing what stars truly were, humans sensed that the sky held something important. Over time, curiosity deepened. Philosophers in ancient Greece debated the nature of the cosmos, wondering whether the stars might be distant suns or something entirely different. In other parts of the world, astronomers carefully recorded the positions of stars and planets, noticing subtle changes that hinted at deeper patterns. These early efforts were not yet science as we understand it today, but they revealed something fundamental about human nature. We're a species that asks questions about the world beyond immediate survival. We want to know what lies beyond the horizon. The invention of the telescope in the earlier 17th century transformed that curiosity into something new. When Galileo first turned his telescope toward the heavens, the universe suddenly appeared far more complex than anyone had imagined. The moon revealed mountains and craters. Jupiter possessed its own orbiting moons. The Milky Way resolved into countless faint stars. Each new observation hinted that the universe was larger and more intricate than previous generations had believed. From that moment forward, astronomy became a journey of discovery that continues today. Every improvement in technology allowed humans to look deeper into space and further back in time. Telescopes grew larger, cameras became more sensitive, instruments capable of detecting radio waves, infrared light, and X-rays expanded the range of signals we could observe. With each step forward, the universe revealed new layers of structure and history. Galaxies that once appeared as faint smudges became vast stellar systems containing hundreds of billions of stars. Clusters of galaxies revealed enormous concentrations of matter bound together by gravity. The cosmic web emerged as surveys mapped the positions of millions of galaxies across the sky. Even the earliest moments after the Big Bang left detectable traces in the cosmic microwave background, a faint glow filling the entire universe. Yet the deeper our observations reach, the more remarkable the situation becomes. The galaxies we observe are not simply distant objects. They are also records of time. Light from those galaxies has travelled across billions of years before reaching Earth. By studying that light, we are reconstructing events that occurred long before our planet existed. In effect, we are historians of the cosmos, reading the ancient signals carried by photons that began their journeys in the early universe. This effort is not merely about satisfying curiosity, though curiosity is certainly part of it. Understanding galaxies also helps answer fundamental questions about how the universe works. The formation of galaxies reveals how matter behaves under the influence of gravity. The motion of stars within galaxies reveals the presence of dark matter, one of the most mysterious substances in modern physics. Observations of distant galaxies help measure the expansion of the universe and the influence of dark energy on cosmic evolution. In other words, galaxies are not just beautiful structures scattered across space. They are laboratories where the laws of physics operate on the largest scales imaginable. By studying them, scientists gain insight into the fundamental forces that shape reality itself. And yet, there is also something deeply human about this pursuit that goes beyond equations and data. The act of observing distant galaxies is a reminder of where we stand within the larger story of the universe. The Milky Way contains hundreds of billions of stars, but it is only one galaxy among perhaps 2 trillion within the observable universe. Each of those galaxies contains its own stars, its own planetary systems, and possibly its own histories unfolding over billions of years. Against this immense backdrop, the Earth is a small and fragile place. Our planet orbits a single star located in a quiet region of a spiral arm within one ordinary galaxy. Yet from this small world, we have learned to measure distances across billions of light years. We have built instruments capable of detecting photons that began their journey when the universe itself was still young. The atoms inside our bodies were forged in ancient stars, and the elements that make up our planet were created in stellar explosions long before the sun formed. In a very real sense, the study of galaxies is also a study of our own origins. The story of the universe is not separate from the story of humanity. The processes that formed galaxies also created the stars that eventually produced the elements necessary for planets and life. When we observe distant galaxies, we are seeing the earlier chapters of a sequence of events that ultimately made our existence possible. There is something quietly astonishing about that realization. A species that evolved on a small rocky world has developed the ability to understand structures billions of light years away. Through observation, mathematics, and careful reasoning, we have learned to reconstruct the history of the cosmos from the faint signals carried by light, even when those signals began traveling before the Earth itself existed. This does not mean we know everything. In fact, the more we learn about galaxies and the universe, the more mysteries appear. Dark matter remains invisible, its true nature still unknown. Dark energy continues to accelerate the expansion of space, but its origin remains one of the greatest unsolved puzzles in physics. The earliest galaxies revealed by telescopes like James Webb challenge existing models of cosmic evolution. Each discovery opens new questions waiting to be explored. Perhaps that is part of the reason humans continue looking outward. The universe is vast enough that it always contains something new to discover. No matter how powerful our telescopes become, there will always be galaxies farther away, structures more distant in time, and mysteries waiting beyond the limits of current understanding. In this sense, observing distant galaxies is not only about gathering knowledge, it is also an expression of the same curiosity that inspired people thousands of years ago to look up at the stars and wonder what they were seeing. That curiosity has carried humanity from simple sky watching to orbiting telescopes, capable of observing galaxies whose light has travelled for more than 13 billion years. and as long as that curiosity continues, the story of our relationship with the cosmos will continue as well.